This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Consider a three-phase AC induction motor with the following data specified on the motor nameplate. We know this is a 15 horsepower motor with a rated speed of 1765 RPM. It's designed to operate using either 230 volts or 460 volt three-phase AC systems. In the low voltage configuration, each line draws a whopping 39 amps when operated at the rated condition and 19.5 amps in the high voltage configuration. At the rated condition, it looks like it has a power factor of 0.79 and it's known to be 91% efficient. We'll examine motor nameplates and other entries on the motor nameplates in later lectures. We're being asked to determine torque in units of Newton meters and real electrical power input in units of watts consumed by this motor while in operation. Let's assume we're in the high voltage 460 volt configuration. First, the easy part. Let's use the power and speed data to determine the rated torque. A unit conversion demonstrates 15 horsepower is roughly equivalent to 11.2 kilowatts of power. An algebraic manipulation of the mechanical power formula solving for unknown torque demonstrates torque equals mechanical power times 9.55 divided by rotational speed. Substituting in the given mechanical power and rotational speed values demonstrates this motor exerts roughly 60.5 Newton meters of torque at the rated condition. Now the somewhat more difficult part. There are a couple ways to determine real electrical power input. Method 1, use mechanical power output and efficiency to determine real electrical power input. Method 2, use apparent power and power factor to determine real electrical power input. Importantly, both methods should yield reasonably close answers. Method 1, motors consume real electrical power and produce mechanical power. The degree of effectiveness of this conversion is the measurable quantity efficiency. Efficiency is equal to usable mechanical power output over real electrical power input. An algebraic manipulation of the efficiency formula solving for real electrical power input demonstrates real electrical power input is equal to output divided by efficiency. Substituting our given values demonstrates real electrical power input must equal roughly 12.3 kilowatts. Method 2. Motors consume apparent power, of which there are real and reactive dimensions. Apparent power in a three-phase AC system is equal to square root 3 times line-to-line voltage times line current. Substituting our given values demonstrates apparent power equals roughly 15.5 kilovolt amperes. Power factor is equal to real power over apparent power. An algebraic manipulation of the power factor formula solving for real electrical power input demonstrates real electrical power input is equal to apparent power times power factor. An algebraic manipulation of the power factor formula solving for real electrical power input demonstrates real electrical power input is equal to apparent power times power factor. Substituting our given values demonstrates real electrical power input equals roughly 12.3 kilowatts. You will note that the real power figures obtained using the two different methods agree within a reasonable degree of accuracy. That's the point. There's one right answer, and both methods yield this right answer. Alright, now that we've got a basic understanding of rotating mechanical power, torque, and rotational speed, let's talk about direction. As you are no doubt aware, motors and generators are different aspects of what may more appropriately be called a rotating electrical machine. Motors convert electrical power input into rotational mechanical power output. Generators convert rotational mechanical power input to electrical power output. It's really that simple. This simplicity quickly unravels when we start introducing numbers. In order to establish some clarity, allow me to make the first of several proclamations. Proclamation 1. Clockwise is positive. Counterclockwise is negative. This applies to both torque and rotational speed. Consider a motor revolving at 1750 RPM clockwise and exerting 1.4 Newton meters of torque also in the clockwise direction. With both quantities in the clockwise direction, we would assign positive polarities to both torque and rotational speed. An application of the mechanical power formula demonstrates positive 1.4 times positive 1750 divided by 9.55 yields positive 256.5 watts of mechanical power. Now consider this same motor performing the same task only in the counterclockwise direction, i.e. 1750 RPM counterclockwise and 1.4 newton meters of torque counterclockwise. With both quantities in the counterclockwise direction, we would assign negative polarities to both rotational speed and torque. An application of the mechanical power formula demonstrates negative 1.4 times negative 1750 divided by 9.55 similarly yields positive 256.5 watts of mechanical power. What is the significance of Proclamation 1? As these two example problems are meant to illustrate, it means a motor always produces positive mechanical power because torque and rotational speed are always exerted in the same direction. Positive times positive equals positive, as does negative times negative. Motors always produce positive mechanical power. Proclamation 2. Power in equals power out. This is not a new proclamation, but rather a fundamental law of the universe you've probably had ample exposure to by now. This does not mean all input power is converted to usable power, but rather all input power goes somewhere, usable or losses. For the sake of simplicity, let's consider this motor to be 100% efficient. On a very basic level, we know that motors convert electrical power to mechanical power. If this motor was 100% efficient, and it is known to produce positive 256.5 watts of usable mechanical power output, and power in equals power out, this must mean it is consuming positive 256.5 watts of real electrical power. When displayed in this fashion, electrical on the left, mechanical on the right, what is the significance of Proclamation 2? It means motors always consume positive electrical power. Tracking so far? Clockwise is positive, counterclockwise is negative. Motors always produce positive mechanical power and always consume positive electrical power. Let's now discuss the other nature of rotating electrical machines, generators. Generators are driven by prime movers like expanding steam, falling water, rotary engines, or moving wind. Most people can conceptually accept the fact that motors consume electrical power for torque and speed to come out. What a significant percentage of people don't understand is that a prime mover must overcome oppositional torque to spin a generator at a certain speed, and electrical power just doesn't appear from nowhere. Generators consume mechanical power and produce electrical power. Let's deal with these observations one at a time. Prime movers must overcome oppositional torque when driving a generator. If you've ever tried to pull two magnets apart, you'll recall they exhibit a measurable stickiness in opposition to your efforts. Consider a prime mover driving a generator clockwise at 1860 RPM. According to our earlier definitions, clockwise rotation would be considered positive. In doing so, let's say the generator experiences an oppositional torque backwards, let's say of 7.7 kilonewton meters, as it works to force the rotor past the magnetic poles of the stator. In this case, the counter torque opposes the prime mover in the counterclockwise direction. Get it? Counterclockwise oppositional torque opposes the prime mover's clockwise efforts. According to our earlier definitions, counterclockwise torque would be considered a negative polarity. Positive rotational speed, negative torque. An application of the mechanical power formula demonstrates the generator is producing negative mechanical power. In this case, the generator is producing close to negative 1.5 megawatts of mechanical power. Let's again presume the system is 100% efficient. If power in equals power out, this means the generator must likewise be consuming close to negative 1.5 megawatts of real electrical power. What does this nonsense mean? Listen to the emphasis I'm placing on specific terms. The generator consumes negative 1.5 megawatts of real electrical power and produces negative 1.5 megawatts of mechanical power. Wouldn't it be better to state the obvious? The generator consumes 1.5 megawatts of mechanical power input and produces positive 1.5 megawatts of real power output. These statements are equivalent, and yes, the second phrasing is more semantically correct, but stick with me for a moment and explore the utility of the first statement. the generator consumes negative 1.5 megawatts of real electrical power and produces negative 1.5 megawatts of mechanical power. Polarity and consistency matter. If we stick with our earlier definitions, i.e. positive clockwise, negative counterclockwise, and power in always equals power out, we can make some pretty reliable predictions about motors and generators, both of which should be readily obvious. A motor always produces torque in the same direction as rotational speed. Positive clockwise torque times positive clockwise speeds yield positive mechanical power output. Similarly, negative counterclockwise torque times negative counterclockwise speed always yields positive mechanical power output. Motors always produce positive mechanical power. If we assumed 100% efficiency and power in equals power out, motors always consume positive electrical power. Conversely, a generator always experiences counter torque in the opposite direction as rotational speed. Positive clockwise speed times negative counterclockwise torque yields negative mechanical power output. Negative counterclockwise speed times positive clockwise torque yields negative mechanical power output. Generators always produce negative mechanical power output. If we assume 100% efficiency and power in equals power out, generators always consume negative electrical power. Yes, this is admittedly the same thing as consuming positive mechanical power and producing positive electrical power, but if we use this polarity convention, rather than flip-flopping the sides of the equality, it's readily identifiable which role an electrical machine is fulfilling, motor or generator. If mechanical power is the product of torque and rotational speed, both of which have polarity, we can divide an electrical machine into 4 quadrants of operation. Motors producing clockwise torque in the clockwise direction, motors producing counterclockwise torque in the counterclockwise direction, generators producing counterclockwise torque in the clockwise direction, and finally, generators producing clockwise torque in the counterclockwise direction. For example, consider an electrical machine producing 5 Newton meters of clockwise torque rotating at 1140 RPM in the clockwise direction. Both properties are positive. Positive times positive equals positive. An application of the mechanical power formula demonstrates that this is a motor producing positive 596.9 watts of mechanical power. Consider another electrical machine producing negative 3 Newton meters of counterclockwise torque rotating at negative 1730 RPM in the counterclockwise direction. Both properties are negative. Negative times negative equals positive. An application of the mechanical power formula demonstrates that this is also a motor, only this time it's producing positive 543.5 watts of mechanical power. Next, consider an electrical machine producing negative 2.5 Newton meters of counterclockwise torque, although it's rotating at 1600 RPM in the clockwise direction. Torque is negative, speed is positive. Negative times positive equals negative. An application of the mechanical power formula demonstrates that this is a generator producing negative 418.8 watts of mechanical power. What does the production of negative mechanical power mean? It means that the generator is consuming 418.8 watts of mechanical power. And importantly, the prime mover, i.e. the wind, water, rotating engine, or expanding steam driving that generator, needs to be able to produce at least 418.8 watts of mechanical power to move it. Electrical power doesn't come from nowhere. Lastly, consider an electrical machine producing 4.5 Newton meters of clockwise torque rotating at negative 1260 RPM in the counterclockwise direction. Torque is positive, speed is negative. Positive times negative equals negative. An application of the mechanical power formula demonstrates that this is a generator producing negative 593.7 watts of mechanical power, which we all know means the generator is consuming 593.7 watts of mechanical power. I'll readily admit polarity is a housekeeping trick. However, you can't argue with the results. I found this technique really emphasizes the different aspects of rotating electrical machines, motors on one side and generators on the other. Positive times positive equals positive, negative times negative equals positive. These are motors. Conversely, positive times negative equals negative, and negative times positive equals negative. These are generators. Case in point, let's take another look at the speed torque curve for a Design B 3-phase AC squirrel cage induction motor. You'll recall the speed-torque curve for a Design B 3-phase AC squirrel cage induction motor we examined earlier looks something like this, where torque is plotted on the vertical y-axis and rotational speed on the horizontal x-axis. Taking into account polarity, you realize this only presents the motor's operation in the clockwise, or positive direction. If we wanted to be more thorough about this, we could extend this into the counterclockwise, or negative direction. In doing so, a more complete chart might look something like this. In counterclockwise operation, the motor rotates counterclockwise and produces counterclockwise torque. This still results in the production of positive mechanical power, because negative times negative yields a positive value, as does positive times positive. This means these two sections of the speed-torque curve represent motor mode. This shouldn't be too much of a stretch if you've been following the previous conversation. Here's where people kind of lose their minds. You note this chart as presently illustrated is for speeds below the synchronous speed, i.e. the speed of the rotating magnetic field produced by the stator. What happens if some outside force, like moving wind, falling water, a rotating engine, or expanding steam, i.e. a prime mover, grabbed the shaft of the rotor and started spinning it faster than synchronous speed? We might get a more comprehensive speed-torque curve that looks something like this. You know, the more comprehensive speed-torque curves now feature two almost mirror images of the motor modes reflected through the horizontal axis. What does the extension on the right imply? Clockwise or positive speed, and counterclockwise or negative torque. Similarly, what does the extension on the left imply? Counterclockwise or negative speed, and clockwise or positive torque. Both of these regions of operation imply generator operation. Positive times negative equals the production of negative mechanical power, as does negative times positive. You'll again recall the production of negative mechanical power is just a stupid and confusing way of saying consumption of positive mechanical power. This more holistic chart reveals something interesting about induction motors, where the term motor is in quotation marks. They're not motors. They are rotating electrical machines and can be used as motors or generators. Put that in your pipe and smoke it. If this is too much for your tiny eggshell mind right now, relax and fear not. We will revisit this concept in much later lectures on asynchronous generators. The important facts for this lecture remain clear. Mechanical power is torque times rotational speed divided by a constant. Clockwise is positive, counterclockwise is negative. Motors consume positive real electrical power and produce positive mechanical power. Generators consume negative real electrical power and produce negative mechanical power, which again we all know is a confusing and stupid way of saying a generator consumes mechanical power and produces real electrical power. You'd think that'd be all there is to say about mechanical power, torque, and rotational speed, but let's drag this out a little bit longer and quickly discuss the tools one might use to measure these properties: dynamometers and tachometers. Since no one on earth can spell these words, let alone pronounce them, most people refer to them as dynos or tachs. Even if you don't walk away from this lecture fully understanding torque, speed, and mechanical power, you'll walk away sounding like you do if you use these cool slang terms. Dynos measure torque, and tachometers measure rotational speed. There are technically three different types of dynos. The first one being an absorption dyno, which if you think about it is kind of like a punching bag for a motor. It can load a motor up by increasing oppositional torque and measure the torque exerted by the motor to balance this oppositional torque and display it on a meter. Old school examples of this type might be a frictional wheel or a pony brake. A drive dyno is the exact opposite. It produces torque to drive an electrical machine, and it'll display the oppositional torque that the electrical machine is exerting against it. The third type is a universal dyno, which is a combined absorption and drive dyno. Such a device is useful in a lab setting to discuss the dual aspects of motors and generators. There are several methods of measuring speed, but they all fall into two general categories: contact and non-contact tachometers. Contact tachometers are sometimes called tachometer generators, and they obviously physically need to contact the device they're supposed to measure. They produce an analog output voltage proportional to RPM. Slower speed results in lower output voltage, faster speed results in higher output voltage. The output can be read on a needle meter or input to a computer and digitized for later processing. Non-contact methods of rotational speed measurements are numerous. A handheld retroreflective laser tachometer can be used to measure the speed of a rotating mechanical object under inspection. This necessitates a piece of glint tape be installed in the motor shaft to return the transmitted laser light back to the receiver. The laser tack can't be held too close nor too far away if you want accurate results. Resist the temptation of shining this tool in your or your lab partner's eyes. You don't need to pay some unschooled youth $8 an hour to sit there with a laser tachometer to get valid rotational speed readings, because there are numerous automated methods of doing so, all falling under the blanket term rotary encoders. If all we're concerned about is rotational speed and not direction or position, a single Hall effect or inductive sensor on a shaft is more than sufficient to do so. Every time an indicator, the presence or absence of a metal object, passes through the sensor, it detects the presence or absence and indicates it with a pulse, hence the term pulsar. If a single indicator on a shaft passes a sensor 30 times in 1 second, this means the shaft is traveling 1800 RPM. The single sensor scheme has a disadvantage though, because we can't tell which direction those pulses are coming from. A single clockwise rotation produces the same number of pulses as a single counterclockwise rotation. This disadvantage can be overcome with two sensors with a slight angular offset between them. Tag A is in front of tag B, and when the shaft is rotated clockwise, sensor A receives the signal before sensor B in the same line. Opposite if rotated counterclockwise. Sensor B would receive the signal before sensor A. As with a single tag pulsar, the time it takes between subsequent signals at each sensor is indicative of speed. There are varying levels of complexity of this type of rotational speed measurement, and is sometimes referred to as, quite surprisingly, as AB encoding, incremental encoding, and/or quadrature encoding. We'll get to these methods much later. Much later, we might visit absolute encoding, in which each angular position in the shaft is assigned a specific binary address utilizing something called gray code, where only 1 bit position changes for each transition to the next position. For now, just think of these advanced methods as super fancy methods of determining not only rotational speed and direction, but also relative or exact position of a shaft. Alright, that's about it for today. In conclusion, this lecture introduced the concept of torque and examined how torque and rotational speed influence mechanical power. Additionally, we introduced the concept of polarity and how this polarity shell game keeps you track of whether a machine is consuming electrical power and outputting mechanical power in motor mode, or consuming mechanical power and outputting electrical power in generator mode. Finally, we discussed common instrumentation used to measure torque and rotational speed. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.